I'm going to go through some tutorial slides basically that cover how you use the SpiNNaker system, how you connect, and yeah, how you make use of the Python language to run simulations on SpiNNaker. So after that, then you can access the system. I mean, you can access it during the tutorial if you like and try and do some things, up to you. You'll be able to play with a couple of different scripts and tutorials that we have on the system then, and try out some things and see if it all works for you. After we've done the presentation, there'll be me and Christian are here to answer any questions. Feel free to ask any questions in the chat as you go along. If you want to put up your hand as you go along, I can try and answer things as well. Okay. So the first thing is, how do you access SpiNNaker? So you've been sent a link from Bjorn, which lets you access SpiNNaker through the collaboratory. And that is the recommended way of doing things these days. There is also a sort of direct URL, which the collaboratory is accessing anyway. If you want to try accessing that, if something isn't working with the collaboratory, you can do that as well. Either way you get into it, well, sorry, no, only if you go in via this way, actually. If you go in via the collaboratory, you'll be already logged in, and you'll therefore automatically come up with a Jupyter system, and you don't have to do anything extra. If you do go in via this mechanism, you'll be asked to sign in first. Although it's still got the HBP credentials listed, they're out of date. There isn't actually a way to use those anymore, so it won't work. But if you use eBrain's credentials, that will get you into the system. Again, if you're using the collaboratory route, you probably won't see this either, because I think it automatically takes you into the Jupyter Lab interface to sort of match up with the eBrain's Jupyter system. If you're coming in via the other way, you can use the older Jupyter Notebook interface as well, which we've kind of left up there. It doesn't really make much difference from our perspective which one you go for. So if you want to try using either, that's fine. By default, I'll take you through the Jupyter Lab interface because that's kind of the more general one that most people will access, I think. So when you get in, you'll get a screen a bit like this. So this is all the Jupyter system. If you've used Jupyter before, you'll kind of understand this. One thing that's in particular different on ours is we have the SpiNNaker and SpiNNaker Git kernels installed. So the normal Python, there's an old Python 2 kernel potentially on some older notebooks. I can't remember if it's on all of them now. We don't recommend using Python 2 anymore because it's out of date and it's not supported anymore. So you're best to go in via Python 3. If you use the SpiNNaker or SpiNNaker Git kernels, they should be on Python 3 anyway. And they're the ones where the actual SpiNNaker software is installed. So you'll have to use one of those if you want to actually use SpiNNaker. The difference is SpiNNaker has the latest release version, which is about a year old now, I think. SpiNNaker Git has the Git repositories checked out. Actually, when you first run it, they'll probably be the same version, but the SpiNNaker Git allows you to actually update that, which you can do from a terminal, which I'll show you a bit later. If you want to get the later version or the latest bleeding edge version of the software, you can do that. We do run tests on the Git versions every day, so generally speaking, they're pretty stable, so you can use those if you want to. And if you want to access certain features that are not yet out there, things that we're in the middle of developing, then you can do that from there too. Also within here, there are a few folders that are quite interesting. There's a work folder. Basically, ideally, if you store your files in the work folder or the drive folder, I'll come to the drive folder in a minute. The advantage of that is that if you ever need your Jupyter system resetting, the work folder is sort of a more permanent place to put your files, so that should be there all the time. If you don't do that, they're sort of stored locally inside your Jupyter system, if you like. So if it ever gets reset, of course, you won't get access to it. We don't generally reset it without you asking. So, but that also means that you don't necessarily get access to the latest release immediately. So if we do a software release and you want to change, obviously, if you stored all your stuff in work, then that means we don't need to do anything special to update that. There are also these tutorials at the top, which is useful for today in particular. You'll be accessing those later on to actually run the tutorials. They're there in all the notebooks just so that you can play with things, and I'll go into the detail of those later. There is the drive folder here, which is access to the eBrains drive. That should be connected up when you go into it, and you should be able to access all your eBrains drive folders. It's not quite laid out the same as the standard eBrains drive in that we still have all the sort of separate shares in there, but it does at least let you share things then with other eBrains users if you want to. Yes, inside the drive it looks like this. So you've got your libraries, which are all your things, shared with all, shared with groups, and shared with me sort of folders. As I say, we don't sort of have a general shared folder in here yet, which is something that the other eBrains Jupyter does have, but we've not updated ours to match that yet. So, oops, gone forwards an extra slide. Let me just make it go back. Where's that gone? Yes. So yes, as I was saying, to run SpiNNaker example, you need to click on this SpiNNaker thing here, which will open up a new empty notebook, and then you can type in your Pine script from there. There are various things you can do in this Jupyter notebook. You can change the kernel, which means you can switch between SpiNNaker and SpiNNaker Git. So if you've got something working in SpiNNaker or not quite working in SpiNNaker and you want to see if the Git version works with it instead, you can try changing kernel. You can also close and shut down your notebook. This is recommended in general. So if you've got a load of notebooks open, you could have them sort of halfway through a script, which means it might be holding onto a SpiNNaker machine. If when you're finished with the notebook, you close and shut down the notebook, then it should release the SpiNNaker machines as well, which is quite nice. There are things in Jupyter you can do. You can press the tab key to sort of get an autocomplete. So if you're not sure if certain things are available in the system, you can press tab and see what comes up, and it might give you some hints to remind you. You can also use shift tab to get a sort of signature inside a function. So if you're inside a function, you press shift tab, you should be able to see the description of the function inside, which is quite useful for finding out what sort of parameters a function takes. I believe these are still working on the Jupyter system, but if they're not, it might just be an oversight, sorry. But it's worth trying because you can see how things work then. But I'll be covering these functions a bit as we go through the tutorial anyway. You are able to install other libraries inside the system. We tend to use this %pip install. There is an exclamation mark pip install, but that doesn't seem to work very well in our Jupyter system for some reason. But if you use the % install, it does seem to work. So you could install various things in there. As I mentioned before, you can start a terminal session, which means you can sort of, it's like almost like having SSH access into the local servers in Manchester. So you can do that. Obviously, it gives you access to your own individual server, so it's not actually access to any of our direct servers. It's all run inside Docker instances, so you can play about inside there, and if you mess things up, we can reset your instance and not have to worry about upsetting other people. When you get a terminal, yeah, it looks a bit like this. There are some things you might want to do in the terminal. If you wanted, you could run the NRP, because we have the NRP installed in the system. And to do that, you can run these commands. There's a CLE nginx, which starts a sort of web server inside there, and CLE start actually starts the NRP running. And you can then connect through some proxy system inside our Jupyter notebooks. You can actually connect to the web server that's just been started up. And you do it like this. You replace your username in this space here, and you'll be able to access it, as long as you're running the NRP, of course. It doesn't just work without it. And you can then log in. There is an authentication, which I think is NRP user and password, so it's not particularly amazing, because that's, again, only access to your personal NRP space anyway. And when you shut that down, it stops running. The security isn't so critical. If you are using the NRP, there's an NRP storage folder here, which lets you access the experiments inside the NRP and see things happening inside there. When you are finished with your Jupyter notebook, similar to closing down your terminals, it's also nice if you log out, because this actually shuts down your running Docker instance. Clearly, if you're wanting to run something slightly longer term, you might not want to do this, but we do also support a batch service for those longer term jobs anyway. So if you want to run longer term things, it's advised to use that. Apart from anything, the notebook system tends to not run things so well in the background anyway. So it's better to use the batch service for those sort of longer running things. But yeah, if you can log out at the end, that helps us a bit. I think the server will auto log you out after something like 2 weeks if you haven't done that anyway. So of course, running very long running things won't work anyway because of that reason. Okay, so that's how to access the system. I'll now sort of cover our system. I suspect a lot of you know about spiking neural networks, but just in case, I'll sort of cover the basics of it. So spiking neural networks, we kind of have a representation of a neuron which has a sort of membrane here, and you have connections between the neurons, the synapses here. The neurons spike, and that potentially increases or decreases the membrane potential. In excitatory cases, it increases it, so these are all exciting this membrane. At a certain point, that reaches a threshold, and that neuron fires, and that carries on to the next system, the next neurons in the system, in the network that you've described. So fairly basic. We do sort of simulate things at a sort of lower level than that as well. So not only is it just the spike instantaneously, when we simulate the sort of time it takes for the spike to cross the synapse. So when the spike comes in, it causes the charge to transfer across the synapse, and then it hits the other end, so that you can see that in simulations, and you'll see that later on, where say you don't expect a spike to instantaneously affect the following neuron because of this transfer time. Okay, so we use SpiN to describe neural networks on SpiNNaker. This can also be used to describe neural networks on other systems, so it's quite useful. It's particularly used in neuromorphics, so it's used on the brain scale system. But there is support for Nest SpiN scripts as well, and Brian, and even Neuron as well. So you can describe your networks and all these in just using SpiN, and then run them on all these different platforms. There are minor differences between the implementations on these platforms, but mostly you can sort of get the basics for things like the actual neuron populations and projections you can do. And I'll come into what those are in a minute. So the first thing you have to do in SpiN is you import which simulator you're actually going to use, so that it knows which one you're going to use for the rest of the script. So of course, this is the bit that would change in your script if you're using different simulation engines. In our case, you use SpiNNaker. Apologies, someone's trying to phone me for some reason. Yeah, turn that off. So yeah, that's the first bit. You can call this whatever you like. I've used P in this. We quite often use sim in our simulations as well. It's entirely up to you what you use as that variable, as long as you use it consistently after that. So the first thing you do is you set up the simulation. By default, SpiN uses a simulation time step of 0.1 milliseconds, and all these time steps are in milliseconds. On SpiNNaker, we tend to run in real time at 1 millisecond time steps. And what we mean by this is that the simulation time progresses at the same time as the clock. So the clock that's ticking, 10 milliseconds passes in actual time, 10 milliseconds passes in simulation time. That's how we get our real-time runs. We do support other time steps, however, but by default, we'll slow down your simulation. So we'll get time step. If you say a time step of 0.1 milliseconds, we slow down by 10 times. So now your simulation time progresses 1 millisecond for every 10 milliseconds of actual wall clock time. So it's worth noting this. Why might you actually use this different simulation time steps? Well, at 1 millisecond time steps, your simulations tend to be quite coarse. So the movements between time, you sort of see this blocky output when you use plot graphs because things are moving that way. Now, if you've got very precise neural models or anything going on in your simulation that's complex, it might miss the finer details of that. Whereas if you run 0.1 milliseconds, you might get a smoother output from that. And that can be critical in certain neural models on the system, particularly when you're using conductance in our system. It's better to use 0.1 millisecond time steps for the precision. But it does hugely depend upon what you're actually running in your network. You can do 1 millisecond things, time step for very simple things, for example, and it will work perfectly well, even with conductance models. So the first thing you need to do after you set everything up is describe populations. So you want to describe the neurons in the simulation. In this case, I've described there's 4 neurons in a population. It's using a neuron model, IFCURX, which is LIF neurons with current input and exponentially decaying synapses. And I've given it a label. The labels are mostly useful for later on in the simulation when it's reading things back. If you want to read reports, sometimes it's easier to see what's actually been going on by giving the labels to the populations as well. So I can describe the second population, different number of neurons. I happen to be using the same model, but you don't have to. You can use different models on each population if you want to. People tend to use the same model, but it varies. And again, we can give it a different label here. You do have to give them different labels if you are going to use labels. If you don't use labels, it will automatically name them things like population 1 and population 2. So they are given labels automatically. It's just harder to read what's going on later on if you do that. Some examples of the neuron models that we have on our system. We have as I said, the current lift with current exponential. So this looks a bit like this if you're using a sort of fixed input. We also have conductance synapses, as I mentioned earlier, with exponential decaying synapses as well. We have an Izikovich model running. I think we also have Izikovich with conductance. There are a few other different models, but they're sort of the main ones that a lot of people tend to use. We also have input models that are for just providing input to the simulation. So you can have a spike source array, which allows you to define spike times, and that can be in any way you want. You can define the spike times for all neurons, the spike times for each individual neuron in your simulation. Of course, the more spike times you describe, the longer it potentially takes to load onto the machine. So just a warning there. You can also use spike source Poissons. This produces more random output. And again, you can define the rate, which can be the per neuron or a rate for the whole population, which means all neurons are spiking at the same rate. But of course, even at the same rate, each neuron is defined as producing different random spikes. So although the rate on average will be the same, each neuron will potentially produce a different output, which is quite useful for simulation. You can also record then your output from your simulations. Most populations, which are not inputs, support both V and spikes. Input populations tend to only support spikes. You can also record the inputs. We usually call them GSIN, INH, and EXC for inhibitory and excitatory. We use GSIN even though it's potentially current-based synapses as well, I'm afraid. It's just a sort of thing, hang up from previous times. So if you're recording GSIN, you're recording that for any sort of input. But mainly we record V and spikes. They're the sort of most common things to record. Spikes probably even more than V. V is useful if you're debugging models. You want to sort of see roughly what's going on in the voltage. You can see very detailed per neuron voltage traces. Spikes give you every spike that a neuron produces in the simulation. That's quite useful. You can initialize your neurons. What this means is you can set up the initial point which V starts for a simulation. So here I've set the initial V to 60. You can also use random distributions here. So this is our introduction to random distributions here. There's a uniform distribution which goes from -65 to -55 volts as the initial voltage. And you can see here this has made all the different neurons start with different voltages. So once you've defined your populations and you've initialized them, decided what to record, you also want to connect them together to make an actual network of neurons. And to do this in Pine, you use projections. So here I connect population 1 to population 2. I'm using what's called a one-to-one connector, and I'll talk about connectors in a minute. And I'm using a static synapse, which means a synapse which doesn't change weight throughout the simulation, doesn't change at all throughout the simulation. And here I'm defining a weight of 1 nanoamp in a weights are in nanoamps in current-based synapses and microsiemens in conductance-based synapses, just to be slightly confusing. But it works out better in the equations to do that. And then we define a delay, which is how long it takes for the spike to be received by the target neuron. Yet we can have a receptor type in addition to these. So we can say the input is excitatory, which means it generally increases the membrane potential. Or we can also say it's inhibitory, which means when the spike is received, it decreases the membrane potential. So I mentioned there's different connector types. A one-to-one connector means that each source neuron connects to the equivalent numbered neuron in the target. We do kind of number neurons mostly implicitly. If you have more target neurons than source neurons, it only connects the ones that exist. And similarly, if you had this one bigger than this one, it would only connect the neuron numbers that match. So it doesn't matter that they're different sizes, but it does matter in that you won't get the connectivity for every neuron. We also have an all-to-all connector, which, as it says, means that every neuron in the source connects to every neuron in the target. So each of these neurons is receiving from 4 different sources, and each of these is sending to 2 different sources, because that's how many there are. You can use random connectivity with a fixed probability connector, for example. This says that there'll be approximately 10% of all possible connections will exist. So in the all-to-all connector, you saw all the number of possible connections that existed. This one says there's not all of them, there's only 10% of them approximately. And you can change, this one says 50% of the connections will exist. You can also have a fixed total number connector that says that there will be 5 connections in total. So 1, 2, 3, 4, 5, there they are. And if you want to define connectivity very explicitly, you can use a from list connector, and that will say, I will connect neuron 1 to 1. This one says 2 to 1, 3 connects to 2, and 4 connects to 2. So it's very explicit what I've connected here. The downside of a from list connector is similar to spike source arrays. They take time to load onto the machine. So the more connectivity you describe in this way, the slower potentially it will be to run on SpiNNaker. So you're better using the prior connection types. We also have fixed number pre and fixed number post connectors for anyone who knows a little bit about this. You can play with all those sort of connector types and look at the Pine docs to see other possibilities. There is a different types of synaptic types supported on SpiNNaker. I mentioned before this is a static synapse, so the weight is defined and the delay is defined, and they're fixed throughout the whole simulation. If you increase the weight, you're basically changing how strong this connection is between the two populations. So it means it's more likely a spike from this population will cause the post population to spike, a neuron in the post population to spike. If you change the delay, you're basically, it's like you're increasing the distance between populations. That's not a completely true thing, because you can get other ways of speeding up connections between populations, but that's a rougher way of thinking of it, is you're increasing the distances. In SpiNNaker simulations, we support currently delays between 1 time step and 144 time steps. So this means at 0.1 milliseconds, for example, it would be between 0.1 and 14.4 milliseconds. And so it does vary with the time step as well. You can then support different parameters in those synapses. You can support weight distributions, which are random. So you can say the weights are going to be random between here. This is a normal distribution this time. So it has a mu of 0.5 and a sigma 0.1 in this case, but you can obviously play with those parameters. You can then use this directly in your synapse. So you say the weight is a weight distribution now. There are other ones. There's a normal clipped distribution. This is more useful on SpiNNaker because of what I said about the delays. So I've showed this for weights again, but when using delays, you may want to use these clipped distributions to make sure your delays fit in range. Clipped means that anything that falls outside gets redrawn inside, so it gets redrawn again and again and again until it falls within the space. The downside of this is if you select the parameters wrong, obviously you might end up redrawing forever if it's never going to fall into the space. So you've got to be slightly careful what you set the low and high parameters to in this case. There is also a clip to boundary, which means you won't have this problem because it will always clip things to the exact boundary that fall outside. The downside is it's slightly less realistic in terms of numbers, and of course if you choose numbers outside the range, you'll end up having them all sit on the boundary. So you've got to be a little bit careful with those clipped distributions as to what you actually end up getting. We also support spike time dependent plasticity synapses, so you can have plastic synapses on SpiNNaker system. In this case, I'll sort of show you how that works on the system because it can be a little bit confusing as to how things actually run. So in a time, let's say a presynaptic neuron sends a spike, and then the pre-spike is now received at the post-synapse, so it's received here. That actually happens fairly instantaneously on the SpiNNaker system, so all our delays are done after it's received at the synapse within reason. So say now that causes the post, or at some point later, the post neuron sends a spike. There is now a time for that post neuron spike to sort of transfer back down the synapse basically to reach the synapse at the other end. So it's basically coming from reverse. We now consider the timing between the spikes that's going to be considered for STDP to be that time. So it's the time between the time at which the pre-spike arrived here and the time at which the post-spike got back propagated down there as well. Okay, in a similar way, if the post spikes first, it's the time it's taken to go back there, and then the pre-my spike afterwards, and then it's how long, it's the similar sort of time difference. So the time difference is now how long it takes between those two events, but it's always at this post synapse that we're considering that time, because that's where the plasticity occurs. There's also a deferred execution. So when you've got the presynaptic neuron sending spikes and they get received at the synapses before, you won't actually get anything happening until a second pre-spike is received at that synapse. So this time is actually the time, because that's the time that we physically receive it on SpiNNaker. At this time is the time when we actually do the calculations. So at that point, we consider all spikes that occurred after this pre-spike and all spikes that occurred before this pre-spike. And we do our plasticity based on that. So if you only send one pre-spike, don't expect any STDP to happen. That's really the message being conveyed here. So how do you describe your STDP if you're going to do it? You describe it in terms of a timing dependence and a weight dependence. So this is how is the weight going to change and how is it going to be based on the pre and post spikes. You can start off a STDP synapse with a weight of 0 if you want, and you can give it a delay. The delay is not changing throughout the run. So whatever you give it at the start is going to be the delay of that synapse at the end. But the weight, of course, can be changing. So even though we've got a weight of 0 here, you can still have plasticity operating on the synapse. So one of the rules that we support, one of the default rules in Pine, is the spiked pair rule. This considers, as it suggests, pairs of pre and post spikes. You describe the timings here and the height of how much you want the weights to be changing, sort of based on these parameters here. So the tau plus and tau minus describes how this decays, and the A plus describes how big it starts in the first place. And I'll show you how this knocks onto the weight. So this is just based on the pairing of the spikes first. And yes, when you've got a post that occurs before a pre, you're considering the minus cases. So it's basically the pluses are for potentiation when you're increasing, and the minuses are for depression. What we do is this okay, yeah, I'll go back to the previous slide. This produces a value of delta A or minus delta A, depending on which way you're looking at the synapses. So this is not the change in weight. This is passed into the weight change rule to decide how the weight changes. So this just describes how the distance between spikes is changing, how the weight is going to change. The actual way the weight is then changed is by the weight dependence. So this is an additive weight dependence, which is again one of the common ones used in Pine. And this says we can vary the weight between a minimum and a maximum, so between 0 and 5 in this particular case. And the way the weight changes is based on that delta A that we calculated previously. It then multiplies that by W max minus W min. So it's going to, for the same delta A, you're going to get the same change in weight. So if we're doing potentiation, for example, we're going to increase like this. And when we're doing depression, it will decrease by the same size if you've got the same gap between the changes. We can also do a multiplicative weight dependence, and this is slightly more complicated. So it's going to take into account W min when you're doing depression. So if the change in weight is less than 0, the change in timing is less than 0. And if the change in timing is greater than 0, so you're doing potentiation, you then take account of W max and the difference between the current weight and W max. So this means that changes with the same separation might happen, will produce smaller changes or bigger changes depending on where W is sitting currently. So for example, here we did a really big change because W is sitting quite far from W min. So for the same change here, we had a big change in weight. Okay, so I'll take you through sort of what happens when you actually run something on SpiNNaker, so you can sort of understand what's been output in your console when you're running these things, because it doesn't just happen instantaneously. We have to do a few steps before we get there. So first of all, you call run in your simulation, and you specify how long you want the simulation to run in milliseconds. You want this to be in the same sort of milliseconds as you're running this as time steps. So if you're running in 1 millisecond time steps, you don't need a decimal point after this, of course. If you're running in 0.1 milliseconds, you can specify 0.1, 0.2, 0.3, and so on if you want more precise runs. You can run for as long as you like. Things will do what we call auto pause and resume. So it'll run the simulation as long as it can without running out of space on SpiNNaker, then pause it, get your results, and then keep running again. So it's up to you. So when you call run, the first thing it does is breaks your populations down into smaller units and puts them onto places on the machine. So it decides which cores it's actually going to run the various bits of your simulation on. And of course, this might be on multiple chips. This is just showing you on a single chip, but you might split these up so they're actually running on completely separate chips on the machine. Because of this, we then have to route between those different locations. So here we've got a source on 1.1, and we want to distribute it to all these targets. Because SpiNNaker uses multicast, we can do some sort of clever bits where we send simultaneously across the machine at the same time. This here might go to all these locations very quickly, and so on and so forth. And when you get here, you can send to these two locations at the same time. So it's not sending individual bits here, it's actually sending them all at the same time across the machine. There's also wraparounds potentially, depending on what sort of machine you end up with that you're allocated to run on. The allocation, of course, is automatic. If there is a wraparound, you might get routing that goes like this and goes around the machine. It might go down the bottom and come up the top here. So the routing algorithms work out the quickest way to get across the machine. You'll see that happening. Then once we've decided how to route things, we actually generate data. So your population writes data down to disk, and that is stored ready for loading onto the machine. And then that disk, in fact, a database nowadays is used to load the data onto the machine. And it's done this way because we can then use special processes, potentially when you've got multi-board simulations, to load that very quickly. So we can distribute across multiple boards simultaneously, basically, in parallel. And that loads things much quicker than it would otherwise take. Once you've actually finished running, so the run is finished, and you actually get back control of your population. Now you can choose to just get your results and display them, but you may also want to change something and then run the simulation a bit longer. So one idea here is we can actually do, okay, we're going to set the eye offset of a population and then run it for another 50 milliseconds. When you do this, the good thing is that everything was loaded onto the SpiNNaker machine before, so we can actually just send the single change and then run the simulation again. So the second run will be a lot quicker when you do this. So once you've actually finished running and you've done as many runs as you want, you can then get data out of the simulation. And you do this by everything that you recorded. You say get data with those things that you recorded. If you say get data with something you didn't record, it gives you an error. If you say if you fail to get data of something you did record, it doesn't matter. But of course, those things are extracted from the machine anyway. So after the simulation is finished, it will extract all the data it recorded regardless, if you want to get it or not. So the get data here is actually, although it's shown here getting from the machine, it's actually already done that bit. It's stored in a sort of local space. So it's getting the data locally. So don't record things that you don't really need, because it just wastes time in the simulation. Okay, so once we've got those results, we have to understand them. SpiNNaker records using a format called Neo. Neo records things in a block. The block contains segments. The segments are actually, Pine has a reset command, and if you call reset, you get a new segment of data. If you don't call reset, everything will be in segment 0. So most often you'll see in our demo scripts, things are recorded, things are held in segment 0. So you say, whatever your recorded data is, segment 0, and then you access the various bits of data. The data is then stored in these separate bits. So you have spike trains, which store each of the spikes, and then there's an index for each neuron. So in neuron 0, you actually get the times at which neuron 0 spiked, and 1, you get the times at neuron 1 spiked. You get empty arrays here when there is nothing for that particular neuron. So if neuron 1 spiked, but neuron 0 didn't, you'll get an empty array here and array of spikes there, spike times there. You also have analog signal arrays, although I have a feeling Neo might have changed that now to analog signals, sorry. So it may not be analog signal arrays anymore. You might have to say analog signals, sorry. And what you get is quite similar. The difference is that each of these arrays, one for each neuron, contains a value for every time step. So generally speaking, this will be a value for every time step, certainly in voltage case. So that's telling you the voltage on every time step that was recorded. One thing to note is if you do something which causes your simulation to spike in every time step, you may notice the neuron voltage doesn't appear to change. And the reason for this is that every time step, the neuron voltage goes up and comes back down and goes up and comes back down. But of course, that's it only recording it once every time step. So it records it at the start of the time step. It's not gone up yet. It processes the spike, processes the incoming spikes, causes it to spike, goes back down to that time again, records it at the next time step, and so on and so forth. So what you'll see is just a straight line. So just a warning on that one. I've seen people fall into that before. So once we've got our data, as I said, you can access these. You can say, in fact, I've used analog signals here. I must have got a mismatch of slides there from some previous talks. Sorry about that. So to get your V data, for example, you say data.segment0.analog signals will give you that data. Spikes is in data.segment0.spike so it's normal Python access at that point onwards. You can then choose to plot these values. So you can use matplotlib. Matplotlib's installed and it works on the Jupyter notebooks well. You say create a figure, plot the times against voltage. V0 times against V0 will give you something like this. So this gives you all the outputs for neuron zero's voltage. Similarly with spikes, you can do the same sort of thing. The difficult thing with spikes here is you potentially have to say you want to define the y-axis here. So what do you actually want to call the spike? Because the spikes only contain times. So when you say spike 0, you're going to get nothing on the y-axis. So you need to define a y-axis to actually get that out. So that's if you're using the data raw. It turns out that Pine has some plotting for Neo directly built in. And here you can actually just say, okay, make me a single figure which has all the analog signals in. You do the star notation, which is something you can get out of Python. It basically means expand these arrays into individual values, individual arguments for this panel. So this panel then has a list of different outputs. And then you can also just pass in the spike trains. The advantage of that is then it knows which neuron indexes. It can read these internally and produce nice plots, which is quite good. You can also get the weights and delays out of a run. So if you've got a projection, you can say get the weight and delay as a list, for example. This is useful after STDP, so you can see how the weights change, and it'll look something like this. So although you said get weight and delay, the weight and delay are the third and fourth items in each of these elements. The first two are actually the source and target. So it's saying there was a source and target, 0 and 5. So this is also useful if you've used a probabilistic connector. You can see what your connections were, and then it says what the weight and delay was in this case. Of course, even in STDP synapses, you're not going to change the delays, so they tend to be quite uniform, but the weights may have changed quite a lot. You can also get the weights or the delays as an array. This then gives you an entry for each source and target. I think it's source down that way and target across the way. And if there is no connection, then it puts this nan value in. So obviously, if you've used a probabilistic connector, you might find that it's full of nans. Don't worry about that. That's just where the connections are not actually made. So it's not 0. It's actually not a number. So you know the difference between a 0 weighted connection and a not existing connection. If you want to read more on the Pine system, you can do so. There's some instructions there. And as I say, we don't cover absolutely everything that Pine does, but we do quite a lot nowadays. So you can see all the different ways that you can do things in Pine. I do also have a quick thing on live input and output. So because SpiNNaker is a real-time system, it's often used for robotics. So You can do things with live input and output, and there's a tutorial on the system about that. I'll just sort of cover some brief details on that. What you can do, for example, is you can inject spikes from an external system into SpiNNaker. So you can do this over Ethernet. That's what the spike injector does. And what we do is we create a population with a model of spike injector, and we can call it what we do need to give it a label, because I'll show you later on that's how you couple this together with the thing that actually does the sending. On the thing that does the sending, you call a function called send spikes, and I'll show you that later on. And yeah, so the thing that does the connection, in fact, I'll show you now, is this this connection here. This is a live spikes connection, and it says we're going to send with a label injector. So you have to match up those labels on the system to make those two things connect together. When you call send spikes, you say what you're going to send it to. So you're going to send it to the label injector and which neuron ID you're going to send. And it sends the spike immediately, so as quick as it can, using multicast. So it sends it into the system over Ethernet, and then multicast is used across the SpiNNaker board to actually receive those spikes. You can also change the rate of a Poisson source. So if you add a Poisson live rate control, so this is something you do in the SpiNNaker script, you can then set it so that you can change the rates during the simulation. And you use a similar thing to the live spike connection. You use a SpiNNaker Poisson control connection, and you say, I want to control the label input with this. So again, you need to match up these labels. So this is where a label is very important. When you call set rates, it does a similar thing. You say what the name of the population is and which neuron you want and what rate you want to set. So the rate is in hertz. And you send that here, and this goes again over the machine to the appropriate places and sets the rate of the Poisson source. You can also get live output from the simulation, so you can activate live output for. This will send live spikes then. You define a receive function, which is going to receive these in your simulation. Similarly, you use this live spike connection. You can actually use the same connection if you're going to do send and receive. So you use receive labels in this one. What you pass in to activate live output for is the name of the population. And then you register this receiver function, and then this receiver function will receive the name of the population, the time at which spikes are received, and the neurons. So it's sending potentially once a time steps. You might receive multiple neuron IDs. So basically all the multicast keys are sent out here and directed out with Ethernet, so you can receive them on the machine. You can also output live voltage from your machine if you want to. So you can say, use a special type of neuron, an external device lift control, we've called it. And what this does is output to a translator function, and the translator function receives multicast keys and translates them into whatever you want it to do on the host. The idea of this is that it might be used to control a robot, something of that sort of nature. So you define this control population, and you put it inside a well, you define it as a population. You say what your lift device model is going to be, and that will probably be this external device lift control. And basically every time step, every number of time steps potentially, it's going to send these messages, which are the output voltage of this neuron. And then it will call the translate control packet in your translator, which you can then tell it what to do with that multicast packet. So on Jupyter system that I mentioned before, you can access these tutorials. There's 0-1 running Pine simulations and 0-2 live input and output. If you go onto that system, you'll be able to just access those. Let me go onto the system a minute, actually, see if I can. I'll probably have to reshare my screen. Give me a second. Let me find it. Got it here somewhere. Jupyter. There it is. Let me just put that over here. I suspect I have to do new share because this is how you do it. Jupyter Lab, that one. So you should be able to see here, I have logged into the Jupyter system, and you can see there's a running Pine simulations and live input and output. So if you want to go onto there, you'll get this here. If you click on this one here, it actually launches basically a tutorial very similar to what I was talking about there. You can read that if you like. If you want to skip reading that because you're happy with the presentation, there's also a load of tasks at the end. The tasks tell you sort of what's going to happen. If you want, you can create your own notebook then to do that, or if you click on those, they actually give you fill in the gaps. So the idea is that you can fill in the gaps here. So you say set up simulated user 1 millisecond time step. So you type in how you do that from the tutorial, and it'll sort of take you through running those. There's also a couple of extensions at the end of these tasks. So if you want to try something extra, you can do that. But as I say, if you want to try it without the fill in the blanks version, you can also follow the description here and try that. There are solutions in here, so if things are not working for you, you can go have a look to help, but obviously it's good to try these things out yourself. Similarly, in live input and output, it's a similar sort of mode. It sort of tells you about how these things work. It does tell you some more details of connecting to devices here, but of course, if you're using it in this notebook environment, the only thing you've got is the Ethernet. And this sort of takes you through that way of running things. And similarly, it's got a load of tasks at the bottom, so you can try things out. The live input and output should work in the Jupyter Notebook for these sort of tasks. So I would say, give it a go. We're here to answer questions as you wish. You can either put questions in the chat, put up your hand, and I'll try and notice that you're putting up your hand. I'll switch the share back to the slide that I had here. So that you can see where it is that you need to go again. But as I say, ask any questions as you wish.